Welcome, dear students. In our study of motion of system of particles, we take on the collision problems. The outline of this is, using the conservation laws of physics, we arrive at a relationship between initial and final momenta of an elastic collision. Further, concisely study some cases. The learner will use the conservation laws to arrive at an expression relating initial and final momenta in an elastic collision and pinpoint some special collision cases. Before we come to the derivation, let us recall the conservation laws of physics. In the absence of an external unbalanced force, momentum of a system is conserved. And the conservation of energy, energy can neither be created nor destroyed, but can be transformed from one form to the other. So, let us now look into what is a collision. The definition of collision is a relatively large force acting for a relatively short time. For example, a bat and a ball in contact. The types of collisions, there are two types. Elastic collision, where the energy is conserved during the collision, and inelastic collision, energy is not conserved. For example, you have a ball hitting the bat and bouncing back is an elastic collision, or a ball hit on the wall bounces back is an elastic collision, because it comes back with the same kinetic energy. But if we have the same ball sticking on something like a sticky substance and the motion stops, in this case we have a perfectly inelastic collision and energy is not conserved. In fact, kinetic energy is not conserved. Let us now look into one elastic collision. We have the mass m1. We have the mass m1 with the momentum p moving along the x direction, and the mass m2 is at rest. After the mass m1 collides with m2, it is scattered at an angle theta 1, and the mass at m2 is moving along at a direction making theta 2. Let us now apply the law of conservation of momentum. We see the only body moving along the x direction has momentum in the x direction is the body P1 initially before the collision. Therefore, after the collision, the momentum that is conserved in that direction is seen in the first equation, where along the x direction the only body that is having linear momentum is m1, and the momentum that is seen along the x direction after collision is P1 cos theta 1, P2 cos theta 2. Now, cos theta is a collision, you have dropped a projection along here, and we see that this side here cos theta 1 here, considering this triangle theta 1 and considering the time theta 2 here, the motion along this direction component is given by cos theta 1 and cos theta 2. Now, let us go to the next direction, the y direction. Initially, before the collision, there is no body moving along the y direction. Therefore, the momentum is 0, and after collision, we see there are bodies moving along the y direction. That is, we have got the component P1 sin theta 1, the component from the triangle, minus downward direction is negative, we have got P2 sin theta 2. Therefore, we have applied the law of conservation on the two direction, x direction and y direction. Now, we have a small rearrangement. Rearranging this, we can get cos theta, P2 cos theta 1 is brought on this side and P2 sin theta is brought on this side. The reason for bringing that is, if we square these and add, we know that cos squared theta 2 plus sin squared theta 2 is equal to 1, and that is what we are going to use. If you square and add these two, this cos squared and this sin squared theta add up to give you 1, and we are left only with P2 squared. The right hand side also the same thing. You have to square this and add. When you add these two, here also cos theta 1 and cos theta 1 squared, together this side will be adding up to give you this cos squared theta 1 plus cos squared sin squared theta 2 1 will give you 1, and therefore, we have only left with cos theta 1 here. Kinetic energy before impact is equal to kinetic and after impact. We also know that kinetic energy is given by half mv squared, and we know that momentum is also kinetic energy is given, and momentum is given P is equal to mv. If we substitute this in this, we should get m squared v squared upon 2m, that is equal to P squared upon 2m, which is exactly the quantity that is written here. This is the kinetic energy before collision, because it is only the body m1 is in motion and body m1 is having kinetic energy, body m2 is at rest. But after collision both the bodies move, therefore, we have got kinetic energy of m1 and kinetic energy of m2. Now, we have two equations, we have got P2 squared from this equation and P2 squared from the equation 3, what we have derived earlier. We put these two together, and this is the one that I have derived last third equation, and this is the equation that I am getting from 4. So, 3 from 3 and 4, we equate these two and we come to an equation that is given like this. This equation looks very difficult, but it is nothing but a quadratic equation where this represents as x squared, this is x, and it is having the form of ax squared bx plus c. So, x is represented by it is this, which is a quadratic equation in P1 upon P2. So, therefore, this represents x, ax squared bx plus c is equal to 0, and we all know an equation, quadratic equation has roots given by x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. Now, our a is equal to 1, a is equal to 1 here, b is given by this quantity and c is given by this quantity. If we substitute these equations, we get to an equation number 6. From this equation, earlier one, we see that the maximum angle of scattering of the particle can be measured. We see that P1, this is a component, this part is a continuation of this. So, we said P1 upon P2 can be represented like this, an equation like this, m1 upon m1 plus m2 cos theta 1, and this comes here. So, therefore, we have an equation like this, except the quantity under the bracket cannot be negative. If the quantity under the quantity under the bracket square root is becomes negative, it becomes imaginary, and we are not interested in imaginary values. Therefore, what we do is we rearrange this. We also know just now that we know cos squared theta plus sin squared theta is equal to 1. So, we rearrange the whole thing is sin squared theta is equal to 1 minus cos squared theta. In case we put theta 1 here, we can replace this quantity with sin squared theta 1, and therefore, we have the root P1 upon P2 m1 upon m1 plus m2 cos theta is equal to this. From this we get a maximum angle. This quantity cannot be negative, it cannot be negative. Therefore, it has to be positive. Therefore, this statement that you have here, for it at least to be positive, this has to be greater than 0, and therefore, from that we get the maximum angle that it can have. It cannot be more than that, otherwise it will be a negative quantity. Therefore, equation 7 becomes P1 upon P2 m1 upon m1 plus m2 and cos theta m at the maximum angle. At the maximum angle we have this condition, and if this is the condition, the second part of this will become 0, and we have cos P1 upon P2 is equal to m1 upon m1 plus m2 cos theta m, and cos theta m gives you the maximum angle of scattering of the incident particle. Now, with the help of this, we can come to know many more cases. Now, cos theta m can be written, just now we have written cos squared theta m is equal plus sin squared theta m is equal to 1. Same thing can be applied here, is applied here in this cos squared theta m, square root has come this side, cos squared theta 1 plus sin squared theta is giving you this equation. And we already know if the angle is maximum, it has to be less than or equal to m2 by m1. Substitute the value of m2 by m1 in this. If you substitute the value of this, we get m1 squared minus m2 squared upon m1. Now, this equation will help us go through some special cases. Cos theta m, which we have already write, is equal to m1 squared minus m2 squared upon m1 in raised to the power of half. Let us take the first case when m1 is very large compared to m2, as this case. It is very large compared to the small m2. When this is the case, we can neglect this and we have got m1 squared, this m1, this and this get cancelled up to give you almost equal to 1. So, we are going to get this as 1. When can this be 1? When theta m is almost equal to 0. That means the particle is hardly deviating, theta m is equal to 0 and no deviation of the incident particle. The second case is that m1 is big, but not as large, not very large, it is quite bigger than this. In that case, equation 6, which we have already derived in terms of P1 upon P, gives you the two values of P1 and P2. Two cases. Now, there is another special case when m1 is less than m2, when this particle is less than this. In that case, we can have any value between 0 and pi. In one case, in this case, we have got the first case, we have the collision of collision angle between them is 180 degrees, that is equal to pi. In the second case, we have m1 which is not as small as this, but can be able to move it in this direction. We get after collision angle can be between them is 0. It can move provided this is not very small as this, and therefore, we have these two special cases. The next special case is when m1 is equal to m2, when the two masses are equal. Go back to the same equation 6, it gives two values of P1, cos theta 1 is this and cos theta 2 is P1 upon theta is equal to 0. The case 1, it can be shown using the same conservation laws that theta 1 plus theta 2, the angle made by mass m1 and the angle made by mass m2 sum up to give us 90 degrees. That means they move perpendicular to each other. For case B, the head-on collision P1 is equal to 0 implies exchange of momentum, the masses are exactly equal, and what happens is that this particle will move after collision, this particle will exchange its momentum with this, and this will start moving with the same momentum. This will be at rest, initially this was at rest, this second particle hits this comes to a rest and this moves with the same momentum, therefore, there is an exchange of momentum. With this, we have covered some few cases of collisions. And now, dear students, these are some references for you, and thank you for being with us.